Well, good afternoon. It's my pleasure to welcome you to our EOL seminar featuring Ana Barros from Duke University. She's got this huge resume.
Getting old.
So let's see, she grew up in Angola and Portugal, went to the University of Porto, Portugal, where she got degrees in civil engineering, ocean engineering, came to the US at Oregon. HSI is?
Yes, now it's called the Oregon Health Sciences and whatever.
Yeah, something.
Yeah, it used to be the Oregon Graduate Institute. And so for those of you who know atmospheric chemistry, this is where the first methane studies were being done. And so there was the Indian person, I forgot the Indian name, and Rasmussen, who were looking at atmospheric chemistry. This was late 80s, early 90s. So, yeah, so that's where I was.
So you got a degree, master's in atmospheric science, then a PhD in civil engineering from the University of Washington, my hometown, your hometown too, one of your hometowns.
Yes, although I actually did my coursework all in atmospheric sciences at the University of Washington.
Let's see, been on the faculty at Penn State and Harvard before going back to now being at Duke. She's been on zillions of boards: National Research Council, Water and Science Technology Board, Board of Atmospheric Sciences that we know, and Climate, UNESCO boards. Worked for NOAA, been on committees at NOAA, NASA, DOE ARM, and NSF, and numerous awards, including fellows of both AMS and DGU, I understand. So, without further ado, I think I'll just...
Thank you very much.
Excuse me, could you please make your microphone higher?
Oh, that's what you were trying to... Yes. Better?
Yeah.
Okay, great. Thank you so much for inviting me and for coming to hear my talk. So what I'm going to talk about today is really informed by the last, say, 15 years of work in mountainous regions, but the results and the core of the presentation are going to be about recent work that we have been doing in the Andes. And this work was interesting for many reasons, because it allows me to do hydrometeorology, hydrology, a little bit of meteorology, some hydrology, but also because of this unique opportunity to work with ecologists. So there's a huge number of people working in the tropical Andes and in the Amazon, as you must know, in bioconservation issues, counting species of all kinds of fauna and flora, and doing really amazing work in terms of documenting the ecology and ecosystems of the region and so on. There's a lot less being done in terms of climate and weather, and I hope that through this talk I will convince some of you that this is a really important region of the world to work on some of these problems. So this is actually a picture from aircraft down over the Amazon, and you probably came across pictures like this before on the internet. And one thing that's interesting about this is, of course, it looks like a lot of dots in this image, but if you zoom in, you'll actually see that those dots are aligned, are in perfect lines over ridges in this region. And so there are ridges, large and small, and so each one of these lines is actually one of those landscape features. So you can see this, a very strong organization of clouds with terrain. Now, I wanted to show you two pictures, and they are from two different mountain regions, but they look very similar. And I wanted to ask whether anyone had a guess. One is in the Appalachians, so which one is the Appalachians? This one is in the Appalachians. And this one, which looks in many ways similar, but of course the scales are different. This is actually at sunrise from the top of Manu National Park, where we have one of our towers looking down into the Amazon. And so, but as you can see, the point that I wanted to make here is that in some ways, so many similarities. So we do see, of course, these are much higher than here, but we do see these deep level layers of thick clouds and fog. And then, of course, in the distance, a lot of haze. And basically, these kinds of organizations of the large scale topography, the large ridges, embedding in the smaller ridge valley variations. Now, actually, this is a zoom into the region where we're doing our some of our observations and where we have actually centered most of our model simulations. And this is the station of Waikecha that I was talking to with Wenchao Liu before. This is a research station that actually has a canopy walk, so you can walk in the middle of the canopies of these trees over the big valley. And so this is what the clouds look like in the valley in the daytime, in the early afternoon, and then what they look like. Sorry. Oh, I forgot. Well, there's one pretty much like this that would show you how they look like at sunset. And so what you see is that embedded in that large-scale feature that I was showing in the other picture, you see also this, this sort of similar feature of deep fog forming in these valleys, and then these other clouds that are at higher elevations along ridges and so on. The importance here is that we're at about 3,300 meters, and we're measuring rainfall at about 4,000 meters, on the order of 2 meters of rain a year. And so you can count in the fingers of your hand how many of those rainfall events are actually of convective origin at all. And so most of the rain that is recorded in this region is actually very light rainfall, and it's associated with these very strong diurnal cycles of low-level clouds basically hugging the topography. And it's essential for these ecosystems, because this is what the cloud forest looks like. And this at higher elevations, this is very different from the rainforest-like trees at lower elevations. So in the talk, I'll be showing you some observations from the Andes and also from the Appalachians. Then I'll show you some WRF simulations that we did before, and with many thanks to a field campaign that was conducted many years ago. Julia Pagel, I believe, was one of the lead scientists, that involved aircraft and some measurements in this region of the world, and it was really essential for us to be able to do our research. And then I'll be looking at some scaling feedback behavior in the model, look a little bit at the regional context and why we need to be observing on the headwaters of the Amazon, which is what this region is like. So this is a picture. If you look at Science, I believe it's from this week or from last week, there's actually a big feature article about this interplay between the Andes and the Amazon basin, but looking at it from a paleoclimate perspective. And so this is one of the pictures that they use in that feature. And this ridge here is actually the ridge where we have distributed our towers. So we have very simple towers here. It was a lot of work to set them up, but they're really very simple. They're basically 10-meter standard towers with rain gauges that are well-maintained, well-calibrated on top. And so they are above canopy over these at the different elevations, relatively collocated with patches where ecologists are counting leaves of trees and doing other type of work that ecologists do. These are two of my graduate students doing the hard work of setting up rain gauges in this region. So this is the Kojnipata network. And one of the features that I wanted to show you that's really important, these were preliminary data from our first observations. But what's really interesting is this difference between the region, the valley, and the cloud forest region, and with this very strong peak in the number of observations of rainfall events recorded in the mid of the day, which is actually very similar to what we see, for example, in the Appalachians also. Now I wanted to show you, just because we always think that in remote places, hard places to get to, we have satellites, and satellites are wonderful, but this is an example of the not so wonderful parts of satellite data. So this is a PDF of our observations in our network against the TRIM rainfall estimates, and we're really using focusing on the TRIM PR observations. And so what you can see is that the satellite really tends, to see mostly very, very light rainfall that is not light rainfall, right? And so we're missing very significant number of events at intermediate intensities. But of course, interestingly, we're also missing all the very large events. And also the very low events, right? So it's a sort of a PDF distribution that is not consistent with what we know is the actual diurnal cycle, what the extremes look like, and so on. And it's wonderful because it's better than anything else we have. Yes?
For clarification, this is the average then of all the data that you showed previously?
No, this is actually, we do very careful works. So Chuntao Liu, if he actually identifies, the core center of each precipitation feature and associates with each precipitation feature a certain area and a certain rainfall rate. So this is based on algorithms, of course, and that's exactly how careful work we do. We localize those with our rain gauges. So of course, you'd expect some spatial variability given the spatial resolution. But, it's overall, in terms of the composite, it shows pretty well what's going on. Now, if you look at in this case, we had 13 years of TRIM observations. What I wanted to point out here are two important things. One of them, we already went through that. There's a very large error and actually not predictable in terms of the spatial variability of the rainfall accumulation. But when we look at the spatial distribution, this is really enlightening in terms of looking at how the precipitation features are organized in the landscape. And I hope to convince you as I show you further analysis that this is not by chance, and there's a very close relationship between these spatial patterns and what the topography looks like, and in fact how the vegetation is distributed in this area. One important effect that you'll see later, of course, is this sort of drop. Right, you can see here like a no man's land in terms of convective features, just on the backdrop, a sort of a rain shadow effect on the backdrop of the easternmost foothills of the Andes. And this is very important because vegetation actually follows the sleet and organizes in that way. Now, you can look also at other images, and you see this feature actually showing up in cloud fields, taken from aircraft, and you also see this organization that I was telling you about these cumulus clouds, which are basically organized along ridges on the Amazon side of these mountains. And as you can see in the back, is basically a sort of a localized rain shadow effect. Now, we started working in this area actually just out of curiosity in 2006 and 7 and 8 and so on. And so we did a lot of climatology, looking at infrared data analysis, and then looking at also precipitation features from TRIM, and trying to really understand, can we see any signs of diurnal cycle, and what are the spatial patterns. So this is, for example, in the middle of the afternoon, you can see the very cold brightness temperatures over the altiplano, and and so much warmer features down here. But what's interesting is, and if you look at the differences in the spatial distribution of deep convection versus just warm rain with shallow, maybe embedded convection in them, you see that this region here is this region of the much warmer temperatures, of course, and this region here is the region of the very cold temperatures. And then what I want to point out is this day-night contrast. So you do see in the landscape this big change between the spatial organization during the day and then the spatial organization at night. So now you can see where the cloudiness, the the cold clouds are. And so basically located at the foothills of the Andes, and you see that basically in the Altiplano, there's very few. And of course, these are composites over the entire trim era. So, there are a few, but it means that it happens once, once in a very long while. And so you see that along the valleys and at lower elevations, we see a concentration of precipitation features. So there's clearly a very strong diurnal cycle. It doesn't mean, I used to think that we were seeing basically downslope movement of convective activity actually along in this region, and now I'm convinced that this is not the case at all because these mountains are so complex, the 3D geometry is so complex, but at least we can see this organization. And we can take it further. And for example, one of my students, Lauren, she developed a very sophisticated Bayesian model to infer erosion rate across the entire Andes Mountains, actually using information from these precipitation features, but also the topography. So this is a basin which I believe it's in the central part of the Andes. And what you can see, now that we have here marked, so this is the outline of the basin actually, and these are of course very high elevations. This is in the Amazon floodplain. And so what you can see is that these features, depending on the time of day, they are clearly organized either on the ridges and then at nighttime coming in and coming down, and you can find them in the lower valleys, along with observations of very strong diurnal cycle. Now, if we do a statistical treatment of this, what was interesting to us is that in hydrologies, we look at river basins and we look at the river network in them. And so we classify that river network based on first-order streams, which are the smaller ones, the first ones. And then when two first-order streams get together, they create a second-order stream, and so on, right? And so we create second-order, third-order, and so on. So what we did here was to look at all these watersheds that we looked at and basically look at the distribution of the different streams with elevation. So this blue one is order 1. So these are the smallest streams everywhere in your landscape. And when you look at what is happening here, these are the PDFs of precipitation features from trim. And so what you see is that if you look at the PDF of the first order streams and the PDF of the stream network, they are very, very strongly related. So you can see this very strong association between precipitation, of course, and erosion, even in these mountains that have very strong other types of geologic forcing. So what this is suggesting, and we actually know it's a fact, is that there are numerous very active earth movement in this region, lots of landslides, lots of debris flows, and so on. And for example, in that valley that I was showing you before, where we have our observations, 3 years ago, there were 200 landslides in over one night. And that's how basically this landscape evolves and changes, right? But now I want you to think about this a little bit. So we're talking about scales on the order of 5 or 10 kilometers, right? And over say 5 kilometers by 50 kilometers, and we're talking about 200 landslides. So basically major storm systems coming through and wiping out the entire landscape. And that's what that really extreme event looks like in this region of the world. So we do see all of this organization and so on. And I wanted to show you some other types of organization that we have found in our observations. This is now from the Appalachian Mountains, which, as you know, are the lower mountains on the East Coast. But they're very nice, very interesting. The highest elevation here is about 2,500 meters. So in comparison with the big Rockies, they're really almost like a speckle in the map. But they're very interesting because they actually show very complex topography. And so in this region, we have been looking at the spatial variability of microphysics, and we have been looking at spatial and temporal variability of rainfall, and basically trying to make sense of what are the processes that are controlling precipitation, diurnal cycle, and so on. Now, one thing that's very interesting that we found here is that, and this is just a typical case that shows very well what I'm talking about, is that when you have large-scale storm systems coming through, so very fast, powerful systems, they come through, and of course, this is very small topography, right? And so they come through and they wipe the whole thing out. They're very fast. And so we pretty much, we see some spatial variability in rainfall amounts, but in some cases, we don't see any spatial variability almost at all. So it's basically, it's really a front wiping through, right? But then if you look at other types of events, for example, in this case, you see that there was a more localized small-scale event. And so in this case, these are valley stations, and these are ridge stations, almost side by side, so in the same ridge-valley feature. And so what you can see is that look at the difference in the amount of rainfall in the valley compared to what was observed over the ridge. And so we see this a lot, actually, all the time, and it's controlling a lot of the rainfall that's observed in the Appalachians. So if you looked at it from the point of view, in this particular case, of this one storm event, of the big frontal storm, there's not significant difference among them. But if you look over a three-day period, and in fact over the entire year, you'll find that there's a huge difference in the amount of rainfall between valleys and ridges, and it's actually the opposite way that one would normally expect. So nothing like standard book orographic effect happens in this region of the world. So we conducted some paired observations with MRRs and these Duometers. And one thing that was really interesting for us, we had already seen this, and if you do field work in this region, you do see the very deep fog banks developing, and we have pictures of that. But what you can see here, these are these Duometer observations. So the colors are the number concentration, and then here this is size of the raindrops that were observed. So this is over a ridge, but I actually want to compare this another ridge nearby with a valley nearby. So if you look at these two and you compare same exact period of time, the first thing you notice is that this one is much redder, right, than this one, except for the case of this one storm event, big important storm, large storm that came through. Otherwise, what you see is that we see every day, even though the rain gauges were not getting any rain, we actually see very, very persistent diurnal evidence of these, of large concentrations of drops. And the other thing you see is that they are much larger, right, and higher numbers at lower elevations. And this is a case for a day with absolutely zero rainfall recorded at any rain gauge, and we had 3 paired rain gauges, so there's no excuse to not having at least recorded some. And you can see the difference between what was happening in the ridge and what was happening in the valley. So in terms of the typical diurnal cycle of microphysics, of hydrometeors in those fog features. And low-level clouds in the case of the ridges. So what does this mean in terms of the regional water cycle? So these are cove forests in the Appalachians. And so whenever I write a proposal on the Appalachians, I always say, oh, this is the region in the US with highest number of different species. And actually, there's more species of trees and plants in this region than the entire European continent. So, but those hotspots of biodiversity here, interestingly, as opposed to what happens in the Andes, for example, they are located at the bottoms of valleys in these coves. And so those coves are immersed, often immersed in these fog systems. So we installed, and if you look at the diurnal cycle of drop size distributions, this is from one particular location, but you can see them like this everywhere. This is nighttime. This is at the end of the day. No, this is actually not a diurnal cycle. This is as a function of rainfall intensity, I'm sorry. But what you see is that there's always a very large number of small raindrops in these regions that we count. And this actually is coincident with diurnal cycle. That's why I was saying that. So overall, we had about 40 rain gauges that we distributed carefully and intentionally over at very high elevation sites, over ridges. Just to give you an idea, before we installed our rain gauges, there were only 2 rain gauges in the East Coast above 1,000 meters of elevation. It's hard to, to believe, but it's true. And so after doing very careful measurements over about 8 years that we have been there by now, what you can see is that if you look at these rainfall intensities that have an intensity of less than 3 millimeters per hour, of course, the contribution is much less in the summer, but in the winter it goes up to 65 and 70% in the inner mountain region, in the Blue Ridge and in the Great Smokies. And so basically what this means, and these are typically not captured by rain gauges. So basically about half of the water cycle is actually not captured if we're not doing good measurements. So now we go down to South America, and I hope I'm not over too fast or too slow. And so in our region, in Peru, we were looking at some of the evidence. Of course, we didn't have the same type of sophisticated, organized observations that we had in the Appalachians, but we see the same sort of behavior, right? The same sort of diurnal cycle, same sort of spatial variability, and so on. And so we wanted to really look at the hydroclimatology of this region, which in the wet season is highly controlled by the position of the Bolivian high, and in the dry season, and also by this feature, by the low-level jet, which is well discussed and covered in the literature. So based on climatology, and we selected 5 cases for which we actually also had some Saljax observations, and that's why Saljax, was so great. It's the one experiment that 15 years later is still paying off in terms of the observations. We isolated 5 different characteristic hydrometeorological regimes that control the rainfall, and the weather in this region. So the first one, so these are 200 millibar geopotential heights. This is what it looks like at the surface. And so we have a weak low-level jet case and a strong low-level jet case. This is during the wet season, during the monsoon, and then 3 different dry cases. This one is in the transition season. This one is associated with cold intrusion from this area. And this one is basically a clear, dry, cold day, for the region in the winter. So we're going to look at these hydrometeorological regimes, and to do this, we used WRF. And actually, my student was benefited from coming to NCAR for 3 or 4 months, and he worked with Fai-Chen and Mike, and so he actually benefited a lot from that interaction. But so basically, what we designed was an asset simulation, and here in domain 3. The simulations were conducted at 1 kilometer resolution. And so the first suite of simulations was to basically just look at whether we could reproduce in any way those 5 events are representative of hydrometeorological regimes that we were interested in. And then after that, we did some other studies where we modified the land surface. And so just for future reference, whenever we have the control results in the future slides, they are presented with a very thick line, and this is, the other simulations will be with a very thin line. So remember the slide that I showed you earlier? These were for the weak low-level jet conditions and strong low-level jet conditions together, because those are the 2 regimes that control rainfall during the wet season. And so basically, this is what it looks like over the trim, the trim region, the trim era. And this is what the model, what the WRF simulations look like. And I thought this was actually really good, because we can get, for both cases, basically the convection happening in the exact band that you would expect it to happen in this region. So I was very pleased with that. We also see in the case of the weak low-level jet, the penetration of the convection for these dates exactly where you see it from looking at satellite data and so on. So I was actually incredibly impressed by how well the model did, considering the complex orography in this region. Now, one of the problems, of course, is that we're doing very well over the mountains and maybe less so over the upwind low-level area. Now, these are results from basically straight line analysis that we did in this region, looking at basically at the different air parcels that leave the same point at different times of the day and basically where they end up, right? And so one of the things that you find, that you discover from doing this kind of straight line analysis is that actually the deep convection that we see in the model and that we see in the observation seems to be coming all from the Amazon floodplain. So we don't see any sort of downslope movement of those features. Now, we were very interested in understanding, though, what is the role of vegetation in this context, and also, of course, there are issues with how we nested our grids and so on that could be discussed. Now, if we go into the inner region, in the inner mountain region, and we do the same sort of straight line analysis, what you'll find is that depending on whether we're looking at nighttime or at daytime, as you see, we get actually, and we did this for many different geometries and so on, that's actually very complex distribution of an air parcel that was at any point here, basically, but it left between 6 and 9 a.m. and ends up there, whereas, for example, this one that left in the middle of the afternoon ends up at the headwaters of this valley. So what you see is really very complex 3D spatial redistribution and reorganization of the air parcels. At nighttime, though, you see this one who left basically between 6 p.m. and 9 p.m., this parcel still actually gets up there, but all the other ones are actually moving down as you would expect. But so the question is, at what time and where in this complex mountain range we actually see this day versus nighttime switch, deep convection versus shallow convection, and so on. So how can we, what are the mechanisms that are actually governing this, the arrangement of these parcels? These are actually air parcels leaving from the sides of of the valley. I will not spend a lot more time, but I want to point out something. So we're doing all this analysis. It looks really interesting, but I wanted to point out the kind of scales that we're dealing with, right? When we're resolving individual convective features, we're actually working at pretty coarse scales. So one of the things that we did, actually my student did, was to look at the entire results of these simulations and did some scaling analysis, starting with TKE, looking at individual speeds and total water content and liquid water content and so on. Basically try to understand how is the model scaling, basically is the model capturing observed scaling that we know from other observations elsewhere. And what is the effective resolution of the model? What can we really say from this, from the model? So interesting results, actually. These are results for the total water content. And what you see, this is the E-dry simulation. So this is the very cold, dry, simulation for the winter case. And when you look at the way the total water content in the column aligns itself with scales, you see single scaling, but what you see is that the slope actually has nothing to do with -3 or -5/3 or anything like that. It's consistently -2. But it's interesting because you actually follow this scaling behavior through the entire, through the model, through all scales in the model. So basically our approach of interpreting that the model resolution is about 4 or 5 delta x, in this case works very well. But then if you look, for example, at the weak low-level jet simulation, and we're looking at 7 a.m. local standard time, and so basically this is still at the beginning of the day, and then we look at what happens at 7 p.m. that I showed you where we have those very deep convective towers develop, then what you see is that at 7 a.m., we see the same scaling behavior that you see in the dry conditions, in the dry cold conditions. So basically, and we have the same sort of effective spatial resolution in our resolved scales in the model. However, when you look at what happens in the case where we have widespread convection and so on, we're actually very close to the -5/3 plus the intermittency correction in the scaling behavior. And furthermore, what's interesting about this, and so what you see is that during these simulations, we're varying between different types of scaling behavior depending on the stability conditions of the atmosphere. And others have done this type of analysis, looking at nesting and so on. However, what's interesting is that, so the effective resolution of the model, though, is actually changing as depending on the dynamics and in the stability. So for example, in this case, and we actually identified those points of scale break, and so it can go up to 15 delta x or even higher. So this creates problems in terms of our interpretation of what's happening at low-level values and how we're resolving the lower part of the complex topography, which has much, much smaller wavelengths. So this is the fallacy of thinking, oh, I ran WRF at 1.2 kilometers, and so therefore I'm doing really well. Well, it seems that in terms of the actual physics, the scaling behavior is varying dynamically during our simulation, and so it's not true that it's 1.2 kilometers at all times. So another sort of test that we wanted to do was to really look at land-atmosphere interactions, which have been looked at in many different ways, and have an expert here in the room, but really focusing on the issue of energetics and try to think about how much of what goes on can we really attribute to vegetation and to evapotranspiration specifically. So my student this is really his PhD thesis, so he spent a lot of time. This is Xiaoming's son, who's now at Texas Austin. And so basically, he was able to map the entire NOAA and RMM5 system into a simplified system of equations so that we could better control what happens for each one of these variables. And so then what we did after this was I believe it was every 0.1 second or every 0.2 seconds, we basically replaced every variable that was dependent on evapotranspiration. We took away all the evapotranspiration out. But still preserving, actually it was at 0.2 seconds, but still preserving what was the surface energy balance for the most part. So we call these the Eti Suppression experiments. And this is very important for our colleagues in ecology because they think a lot. They spend a lot of time thinking about what's going to happen to mountain forests with climate change, right? So in the past, with increases in temperature, you are expecting to see these shifts in vegetation species moving upward, right? And for example, this is actually not happening at all in the central Andes. The tree line is almost like it's drawn in stone. And so understanding what happens as we have these changes in climate vis-a-vis evapotranspiration are very important. What they are seeing, though, in this region are lateral shifts. So basically, species are moving laterally and moving actually north. So what we did then, to do those experiments where we basically pulled out all the Eti, this is the band over which we pulled out all the Eti. So it's basically the tropical forest, rainforest in the slopes of the Andes in one experiment. And then this experiment was a little bit crazy, I think, but it was interesting nonetheless, was basically we replaced the entire Amazon. We did the same for the entire Amazon. And just to really look at what impacts would be over the Andes, that's ultimately our interest.
You didn't mess with the partition of energy, just moved it.
We yes. And we did all kinds of experiments then because reviewers demanded them based on bone ratio. And yeah, initially we didn't do some of the experiments, but then motivated by reviewers, we did all of those tests. So as I said before, the thick lines are the control with the realistic distribution, and the thin lines are the strip. So the first thing that I wanted to point out is that one of the big differences between what goes on in the Andes, over the Andes slopes, and over the Amazon is sort of clear. Please, I bundled these together so the amounts, the units in the y-axis are not necessarily correct. But this is, so the red lines are moisture convergence. And the blue lines, the blue dashed lines, are actually the contribution of evapotranspiration regionally over our central domain 3. So what you can see is that the contribution of ET in terms of mass in the Andes itself is not important at all when you compare with large-scale advection. But over the Amazon, it actually plays a very important role, as one would expect, and so all the important recycling studies and feedbacks. Now, when we took away the evapotranspiration, this is the impact. So this is the changes in moisture conversions by eliminating that, the vegetation contribution, and then this is what happens actually over the Amazon. And you can see that for all cases, and of course in the wintertime you see very little impact because very little is going on in terms of amount, in terms of the belt. Now, when you look at the implications, first, in terms of precipitation, by taking away that ET along the Andes slopes, you look at what happens in the wet season, and the decrease in integrated rainfall is about 50%. So it took away the evapotranspiration. And so even though the amount in terms of mass is very, very small, as you can see, very strong impact on the model predicted rainfall. And in the other cases, we see very small differences. Actually, in that case, we see an increase over there. But this is really the important message here. So then, if I draw a line along that cross section, and you look, for example, at total water distribution, and this is daytime instantaneous value, I believe, but maximum. What you see, the difference between those simulations that we call strict and the simulations with the full interactive land atmosphere, what you see is that basically very strong reduction in clouds, of course, and also basically much shallower convection everywhere. So a very strong impact, not so much you see in terms of the mass budget, but actually very strong impacts in stability. Now, in this case, you see very little impacts. This is the case of the cold surge, of the summer cold surge. So if you actually look at the differences in Cape, you see also that over this region, we see very strong decreases in Cape, about minus 800 joules per kilogram, and you see both of them during also the wet season, so associated with this change in atmospheric stability. So what does this mean at the Ridge Valley scale? So if we did this at the larger scale, so using our domain 2, you see about the same changes also in Cape and in rainfall, but we were interested really in understanding what does this actually mean at the Ridge Valley scale. And so what we found is that when you look at the vertical distribution of moisture conversions, what you see is actually happening at low levels. There's actually, this is probably it's an increase in stability, but also a very strong decrease in upslope low-level upslope moisture convergence. So this is a very interesting effect of this sort of change. And so what this reinforces to us is this idea that these valleys are actually playing, albeit probably scaled not as exactly as we would like them to be, but they're playing a very important role in actually pulling up this moisture up. And that vegetation is actually playing that role, is contributing the additional instability or low-level entropy that is needed to actually carry this work at low levels. And so, this was a question that I wrote for my ecologists, colleagues. So, to kind of, try to help them understand how important meteorology is, and clouds and rain and climate and so on. Because as I was telling earlier today, you see a lot of these very careful measurements of species and all characteristics and carbon budgets and nutrient budgets and so on. And there's no rainfall measurements along with that, or cloud measurements are, in some cases you see air temperature, but that's, and relative humidity, but that's as far as things go. So when we did the other experiment, though, of changing the crazy experiment sort of thing, where you take away all the Eti from the Amazon, what you see actually is, as you would expect, a very strong reduction of the rainfall in the Amazon because of those very strong feedbacks. But interestingly, we see an increase in the Andes. So on the slopes of the Andes, around the Andes Mountains, we actually see an increase everywhere. And there's a long explanation of changes in circulation that explain that. But I wanted to point out something very interesting that I think is important also for our regional scale analysis of the context of what goes on. So please take this, these were different experiments, but this orange broken line here is basically the realistic case in a simulation. And then these other lines are all cases where we are either increasing the amount of ET, so actually pretending that now all the trees in the Amazon are evaporating way more, and these cases, the colder colors, are basically the cases where we are extracting part of it. So for example, the dark blue is about at the 20% only of the actual evapotranspiration. So what you see, this is rainfall over the Amazon, right? And what you see, it's not perfectly linear, but you do see you have more evapotranspiration, so you have more rainfall. You have less evapotranspiration, you have less rainfall. So this is a lot consistent with the type of feedbacks and land-atmosphere interaction studies that have been done in the past. Now, over the Andes, this is really interesting for people that live in the Andes. Of course, and is that what we see is a shift in the diurnal cycle. So what we see is actually a reduction during the day in the rainfall, and then an increase in the rainfall at night. So overall, the total change in the amount of rainfall is not that impressive, but what's really impressive by making this change is actually the change in the diurnal cycle, which has huge implications for ecology, for water resources, for hydrology, and so on. And so I like to emphasize this point because, of course, this is a region of the world that is going huge changes, right? And deciding who's upwind and who's downwind in this region is going to be, I think, a very interesting international discussion for the next few years. Now, what you see in the case of the Amazon, though, also is between the control and the strict, we do see changes in the vertical depth of convection and in the strength of convection over the Andes. And more interestingly, remember the thick line is the control, the thin line is our modified experiments. And what you see is that for all of these cases, except in the case of the stronger level jet, we see a very strong change in the cloudiness, in the fraction in the convective fraction of cloudiness, which is another way of having an impact, of course, on the surface boundary layer. And actually, we see an increase in both cases at low levels. So in summary of these simulations, basically what we saw was this very important relationship between Eti and upslope moisture conversions, that seems to be consistent with what we have from observations and from our straight line analysis and so on. And then in the case of the Amazon extraction experiment, what's really important is this, that what happens in the Amazon lowlands is actually not just affecting what happens locally, but it's having an almost continental scale impact in that region of the world. So the increase in precipitation, actually, we're not focusing on those areas, but over Venezuela, in the mountains in Venezuela, is actually dramatic. So basically, the idea then that everybody lives upstream or everybody lives downstream, right? And so land use changes, land cover changes, management of the landscape in both regions have very important impacts. Now, you probably have seen this picture. This was from an article in Science in the spring, but this is actually from a Plus One article about a couple years ago or so. And what you see here, these red dots are actually the dams that are in construction, are being planned for the Amazon. And so at this conference, I was at the conference 2 weeks ago in Peru, where there were like 600 ecologists, bioconservationists, all documenting already big changes in the vegetation composition in the lowlands in the Amazon, around lakes, for example, of dams and so on. Because interestingly, they were showing that land breezes that develop at the lake dryland interface are actually affecting how the species choose to organize themselves away from the lake or into the lake, and has implications for seeding, for all kinds of other, we don't usually think about all of that, but that's actually a very complex system, and these interactions are happening at over a wide range of scales. But one important thing, and if you look at that Science article that came out last week, looking at paleoclimate effects and interactions, the Amazon is what is today because of the very strong and rich nutrient fluxes and material fluxes that are coming from the Andes. So that's what replenishes the floodplain and keeps things going, right? So both in terms of water, but also in terms of material fluxes. So basically constructing all of these dams as they are planned. This is, sort of equivalent of building, I think, the Chinese wall, at the Great Wall of China over the Himalayas, because it's a huge region. When you add all of these together, it's actually a very, very long region where basically now you have these reservoirs serving as a retainer of not only water, of sediments, but also of variability, right? Because what happens is that as we construct all of these reservoirs, all that variability, I was telling you about these up and down moving of the shallow convection and the deep convection and light rainfall and so on, all of that, right? It's smoothed out because it's all integrated by going through the reservoir. So the hydroperiodicity that actually explains the complexity of biodiversity in this region is sort of wiped out or smoothed out because of the construction of these systems. And they are very important in terms of energy production and so on. So this is, it's a very complex problem. But what it would be really great if we actually knew how much it rained here, right? Since there are all of these plans and people are designing multi-million-dollar experiments and so on, but we actually don't know how much it rains here, for sure. And more importantly, we don't understand the interannual variability or the decadal variability of that rainfall. Right? So, when we're designing and building systems like this, we're hoping, because they are so costly, that they will function for 50 years or so, right? So decadal variability in the climate is actually very important to understand what would be the actual water yield in these reservoirs, how much energy we can produce. And then to also estimate what are the ecological impacts and what are the measures one can take to actually alleviate and counter some of the negative effects. Now, another important issue, of course, is that I hope that by looking at those very simple experiments of Eti suppression, you can see that also this region here, where the new experiment, Relampago, is going to be looking at this region where there's very, the deepest convection in the world, right? That has been on record at least. So actually, what happens here and here has very important implications for what happens in this region. So this is a very important, a very important boundary. Now, just to show you, and I should stop because it's been an hour, but I just wanted to give you another example. So we complain we don't know how much it rained. We actually don't also know what is the runoff in these regions. So this is a map of the spatial distribution of the number of stream gauges at or above elevation H everywhere in the world. And these are the numbers of gauges. So first of all, as you can see, above, say, 2,000 meters, it's a ridiculous small number. These are world numbers, right? So it's a very small number. And then if you look at this by WMO regions, the Andes is actually region 3. And so as you see, there's about 2 hands full over the entire South America of observations at elevations above 2,000 meters, where most of those dams are actually going to be built. So we don't know the rainfall. We actually don't know the stream flow either, right? And that we don't know a lot, many other things here. So the context then is this idea of a proactive role of Andean forests in their hydroclimate. And how important it is to actually look at this interaction between the land and the atmosphere mediated by the orography. This issue of everybody lives downstream, which was an EPA saying from the 90s. And of course, they were talking about stream water, but and so the importance of these hydrometeors. I wanted to finish with the point that was in my title. So one of the things that I have started, every time I give a talk, I always talk about this Pan-Andean observing system. And I was talking to my colleagues in ecology 2 weeks ago, and you would be surprised how the number of scientists involved in field work in this region. So there's hundreds of field sites with extremely dedicated and committed and excellent scientists doing their ecology work. And so I strongly believe, actually, that we could leverage a lot of that human infrastructure that is already in place to really begin to make measurements and understand some of these processes so we could get better models. If we can get better models, we don't need to go, to have lots of observations, but definitely focus. And these are 3 regions where the density of the high quality scientific work that is being done in ecology is very high, and where I think it's really low-level hanging fruit to go in and do some long-term climate measurements and analysis. And thank you. That's it. Sorry for taking so long, but.
Question. So going back to the Eti suppression experiments, have you guys tried to do like the amount of precip that is like the actual amounts that scale with respect to the amount of ET that you suppress? So like a scatter plot essentially, or a scaling factor that generally holds. So like in absolute terms, 10 for every 10 meters of precip you have, or for every 10 meters of evapotranspiration, you get 5. Or a percentage of precipitation increase.
We actually did some of that, but I was a little bit reluctant in taking those values very seriously, or present them as very solid, just because we didn't do climate scale simulations, right? So we're looking at typical hydrometeorological regimes and say, in this hydrometeorological regime, what was the contribution of evapotranspiration or latent heating to basically change dynamics, storm dynamics, for these events for which we had good observations. So I think we can do process analysis on this and try to interpret. We can do those calculations, definitely.
But you're hesitant.
And you're most welcome to the data. But the question is, can we really scale them up to a climate? Because I think all my talk I was referring to these cascades and these feedbacks and these nonlinear interactions and so on, right? So we're learning a lot from process studies, but I think to extrapolate would be serious. But I think what it shows clearly is that, for example, clear cutting in the Amazon, and especially in the foreland just at the foothills of the Andes, has huge implications for what happens everywhere in the headwaters of the basin. And so, and actually on itself, right? Because it affects how much rain you get in, and so how much runoff you get, how much erosion you're going to get, and so on, right? So it's, and that was, I think, for me, the most important result was to illustrate that, and not so much the actual quantitative. The trend, the change in diurnal cycle, I think that's very important, because it completely changes how, when clouds form, where they form. And so basically the whole surface energy budget, stable boundary layers at night, radiative cooling, I mean, all kinds of things that can have huge impacts on vegetation and on hydrology. And interesting, on this issue of the paleoclimate, so previously, when other climate changes were documented, right, this up and down of the vegetation was trivial. I mean, it happened, it was slow, but it happened. Things moved up and then it moved down, and following what you would expect it would happen. But now there's some evidence, of course, we're talking about much shorter time scales, but still there's evidence of changes in temperature and so on, and the altitudinal changes are not taking place.
You showed us the similarities between the Andes and Appalachians in terms of the valleys pulling in the air and moisture and pumping it out. Would you care to generalize that the mountain ranges in general do that? The work has the work been done in the other mountain ranges in the Alps?
I think they do, and so actually this work, I have to say, was originally inspired by, and I'm not sure I can say his name correctly, somebody from the Austrian Met Office, a paper that I found at a conference where they were looking, this was 2004, I believe, 2005, and so what he was showing was they had the Austrian Met Office service weather prediction model, and they basically did exactly the same thing. They added or took away reasonable amounts of evapotranspiration for that region, and what they saw was when they didn't have the evapotranspiration, the storm wouldn't go in. So basically, you wouldn't have this penetration of convective storm systems along the valley. Actually, I don't know if you're familiar with this work. His name starts with an H. I actually cite his conference paper a lot, but I was never able to find the journal paper with that work, which I wonder if it was just a question of reviewers or they just didn't bother. But it was a very nice, and people in Japan also, some scientists in Japan, and actually we did that for Central Mexico also with a paper that was published in 2005 or 2006. Basically what you look in a lot of these mountain regions in the world, in the Himalayas, even in Japan and in Central Mexico and so on, is that if you don't get this extra lift of at least 2 or 3 millimeters per day of evapotranspiration that really goes to instability, you can't get the...
Is the name Thomas Hayden?
Oh, Hoyden, yes, probably, yes. How do you... Hoiden? And the H with a umlaut or something, right?
Yeah.
Yes. yeah, exactly. It was, very interesting. It really opened my eyes. Yes, definitely.
Could you go back to your first WRF picture? And I think you were mentioning that actually the rainfall follows very much the topography and so on.
it doesn't follow the topography. I mean, the impact, the way we looked at it in an integrated way, it varies a lot, but let me see. So you mean for when we took out this one?
Even further back, you are showing a much smaller.
So the comparison maybe.
I can't see where your first WRF picture is actually. Yeah, the one there. I mean that doesn't to me look like the rainfall follows the topography. I'm looking at the top part here, and it looks like there's a 50-kilometer grid length.
Oh, it's not grid length. You know, the grid length here is 1 kilometer, 1.2.
Yes, but isn't this an effect of what comes from much further out? From your large-scale grid here, these long lines in these structures? From the outer domain that has much
yes,
closer.
of course. You know,
Okay.
there's forcing, you know, coming, of course, because we have our domain 2, right,
Yeah,
is very large.
exactly.
So, you know, so of course, you know, this is just focusing in that region and trying, you know, to look at the spatial patterns in that specific region. So actually, if you look at our papers, you know, there's one from last year in JAS and one in the quarterly journal. We actually show the comparison between the WRF simulations, even at 18 kilometers with the TRIM large scale. And now TRIM has a problem over the ocean, and along the coastal region in this region is not really doing a good job. But overall, WRF does really nice job, actually, of getting the overall pattern. So if you start looking at the small scales and amounts, then that's a whole different question. But it does a good job. So I don't know if I have those pictures here, because those really show how I don't think I didn't put them here, sorry. Yeah, but we have them as a supplemental material in the papers.
We should probably let people go, but thank you
so
again.
much, and for being so kind and so patient and staying extra.
And you'll be here tomorrow, so
Yes.
if people want to find her, Erin's keeping her schedule, I guess.
Yes,
So
thank you.
let's thank Aaron again.